Vector geometry review. So in Calculus 2, we discuss vector basis, section 13.1 to 13.2. We did dot and cross products, sections 13.3 and 13.4, and lines and planes, sections 13.2 and 13.5. We're going to do a brief review of all of those sections before we start the material for Calculus 3. Vectors. A vector is a geometric object that has magnitude, that's the length, and direction. Scalar is a constant in R, in real numbers, which has no direction, only magnitude. Some of the examples of vectors are force and velocity, acceleration, pressure, flux, and so on. So a vector, when we were showing it geometrically, we start from a initial point A, for example, and an endpoint B. So initial point A and endpoint B, and we draw a line between A and B with a direction with the arrow that shows the direction of the vector. So we refer to this vector as AB with a line with an arrow on top, or as vector V, or as vector V, and that arrow on top shows that it's a vector. In the other part is that let's say if A has coordinates xi, yi, zi for initial point, and B has the coordinates x sub t, y sub t, and z sub t, then AB with the arrow on top is just x sub t, x terminal, minus x initial, y terminal, minus y initial, z terminal, minus z initial. And so as looking at this information is both direction and length. So, and all we interested in is direction and length. So I can take this vector and put it anywhere else as long as the direction is the same and the length is the same. It's basically as long as these other v's are, if you see all these other geometric representations are of the same length and same direction, and they are the same vector. Something notation-wise that we use subtly here is when we were showing the difference between the coordinates as x sub t minus x sub I, we also put in this angled parentheses around it. That shows that that's a notation for a vector, basically, with its coordinates. So let's talk about Cartesian representations of vectors. So we draw a vector v with an initial point at the origin O. The components of v are the coordinates of the terminal point P. So here's the vector, starts at the origin and ends at some endpoint, at terminal point, and we show v with the upper arrow to be the same coordinates as that, except instead of parentheses we have this angled ones. So in general, if v is equal to AB with the arrow on top, that is the initial point is the point A, x1, y1, and z1, and endpoint, terminal point is B with coordinates x sub 2, y sub 2, z sub 2. Then V is going to be a point with difference of the first coordinates as the first coordinate, difference of the second coordinates as the second coordinate and difference of the third coordinates as the third coordinate of it. And so basically, if you find the point x2 minus y1, so basically if you find point, not the vector, but point x2 minus x1, y sub 2 minus y sub 1, z sub 2 minus z sub 1. This point, if this is the terminal point and O origin is the initial point, that's exactly the same thing as V. So V is going to be the vector AB, where A is the original point, the initial point, and B is the terminal point. And in here, when 0, 0, 0 is the initial point, and 2 and 3 and 4 is the terminal point, we form the V. Now, what if I put this V in another place on the in the three-dimensional space? And so let's see. I'm putting it, let's say, starting instead of initial point origin, initial point 1, 2, and 2. Then you have to add the 2 and 3 and 1 to 1, 2, and 2 to get point 3 and 5 and 3. And so this vector over here is going to be the same as this vector down here. And so that's that's how you find the equivalent vectors. So let's talk about a few vector operations. First, scalar multiplication. So what is scalar multiplication? It's just scalar multiplication increases or reverses the direction of the vector. It increases the magnitude of the vector or reverses the direction of the vector. And so multiplying a vector v by a positive scalar c does not change its direction, but multiplies its magnitude by c. If c is less than 0, the direction of c is reversed and magnitude is multiplied by absolute value of c. Two non-zero vectors v and w are parallel if they are scalar multiple of each other. And so that means that there exists a scalar c such that v is equal to c times w, or vice versa. And so, for example, this is v, and then 2 times v is twice as the magnitude, and it's parallel. And 1/2 of v is half the magnitude, and it's parallel. And again, another scalar, -2 times v is going to be basically magnitude is twice as v, and the direction is the opposite. -1/4 of v, or -v/4, is 1/4 of the magnitude and in the opposite direction. Now, two more vector operations, addition and subtractions of vector. Algebraically, two vectors can be added or subtracted by adding or subtracting their components. So if I have a, b, c plus or minus p, d, q, then I take the a and p, which are the first coordinates of the two, and I add or subtract them. B and d are the second coordinate, add and subtract. C and D, the third coordinate, add and subtract, and this becomes the first coordinate of the resulting vector, and this is the second coordinate of the resulting vector, and the third coordinate. Geometrically, adding two vectors can be visualized in terms of parallelograms. So if I have v1 and v2, then I make a parallelogram over it, and you may have done this using in physics already. And then I connect this side of the parallelogram to this side of this vertex of the parallelogram to another vertex. And then the teal line is the V1 plus V2. How about the subtraction? In subtractions, you have a triangular method, which is you just connect the two ends, and the direction should be V1. If it's V1 minus V2, then it has to be toward the direction should be toward the V1, and initial point should be at the end of V2. And so you get the orange vector is going to be V1 minus V2. And then let's say algebraically, this was the picture, and algebraically or geometrically, that one was geometrically. What does it mean algebraically for us is that when you have 4 and 5 as the first vector, 8 and 3 as the second vector, addition of the two vector is just adding 4 and 8 and putting it right here. And then for the second component, adding 5 and 3, and adding 5 and 3 with a comma, 5 and 3, which is 8, and that's the second component. So subtracting V1 minus V2 is going to be 4 and 5 minus 8 and 3, and so you subtract 4 minus 8, which is going to be negative 4, and then 5 minus 3, which is going to be 2. And so this is the subtraction. So addition and subtractions of the vectors. Now, how do we find vector magnitudes? We talk about vector magnitudes a lot, but I haven't tried to find it. Vector magnitudes is given by, so first of all, the notation is this double line around the vector. Double line V1, V is equal to the first component to power 2 plus second component to power 2 square root of that. For W, which is a three-dimensional vector, the magnitude of this is going to be just the square root of first component plus 2 plus to power 2 plus second component to power 2 plus the third component to power 2. Okay, so where does this formulas come from? They're actually Pythagorean theorem, and that's all. And so look at this vector V, and this one is 8 and 3 basically. And then look at the x and y value. X is equal to 8, y equal to 3. And in this x and y value over here, when I'm marking it on x-axis and marking the perpendicular over here as 3, and then I can, in this triangle, I can calculate the hypotenuse, and that's basically 3 to power 2 plus 8 to power 2 square root of that. That's this formula again. And very similarly, it can be shown that again, two Pythagorean theorems will give you the value of magnitude of a three-dimensional vector, and by basically first component, this is the first component, x2 minus x1 to power 2 is the first component to power 2, y2 minus y1 to power 2 is the second component to power 2, and then the third component to power 2 and square root of that. This formula also is called the distance formula, if you remember that. So let's talk about a few special vectors. The zero vector is so we show it with 0, and in some books they boldface a vector. And some books put a vector and arrow on top. We try to boldface and put an arrow. So you boldface a 0. You cannot do that in a handwriting. You just have to put that vector sign on top of it, and that means depending on whether or not the vector is in 2 dimension, 3 dimension, or so on. It means either 0 and 0, or 0 and 0 and 0, or how many ever zeros in the vector format. The zero vector is the only vector with magnitude 0, and its direction is undefined, so it doesn't have any directions. There are also known vectors that you may know from other courses, either from physics or from linear algebra. In standard basis vectors in R2 are in again, whether or not you're thinking about physics or other courses, this may come with either arrow, or it can come with a little hat on top of it. You may know that this way better. And so I is first component 1, second component 0, J is second component 1, the other component 0, and standard basis in R3 again. I is the first component 1, everybody else 0. J is the second component 1, every other one is 0. K is equal to the third component is equal to 1. The other ones are 0. And so when you show it in here, this one is I, because look, this is first component 1. It's the terminal point is 1 and 0. Here terminal point is 0 and 1. And then the fun part about the standard basis is that you can write other vectors using the two of them. How? I can write 3 and 4 as 3i plus 4j. I can write -5 and 2 as -5i plus 2j. And that's how we express them. That's another method of expressing vectors, basically. The unit vectors are the vectors of magnitude 1. When you talk about a unit vector, we talk about vectors whose magnitude is R1. And the interesting part about the unit vectors is that they only specify the direction, and that's very useful also. And so let's talk about Cartesian coordinates in R2 and R3. Coordinates represent geometric objects in space by ordered pairs or triples of numbers, so that you can study them with algebra and calculus, basically. You take so when you're talking about R2 is on this side is the real plane, which you have an x-axis and a y-axis. When you talk about R3, you have x-axis, y-axis, and z-axis. And then reference point here is O, or origin, and it's 0.00. It has 2 coordinate axes and 1 plane and 4 quadrant. This one reference point is O, which is O 000, and it has 3 coordinates and 3 coordinates plane and 8 octants.